Assalamu alaikum. So today we're gonna have another interesting class where we're gonna explore more beautiful things about the soil. In today's lecture, we're gonna go through four main points. We're gonna learn about subdivisions in the master horizons. Then we're gonna see how the transitions horizon work. And we're gonna also learn about maturity and development of the soil. And finally, we're gonna learn about one of the most important physical property of the soil, which is soil color. So without further delay, let's go and explore more beautiful things about the soil. In the previous lecture, we have learned about the master horizons of soil, and we have seen that these master horizons, which are 6, tell us a lot of stories, especially about the development. And they are basically a parallel layer in the soil. Each one of them is given by a letter, and we distinguish them as different layer or different horizons because each layer or each horizon consists of a specific property that is different than the one below or above. But today we're gonna learn something more even interesting. I would like you to pay attention to the following two pictures. Now you have case A and you have case B, and I want you to look at the horizons. You would see something different here. You would see that there is a horizon that is repeated, but it has numbers. So where these numbers exist, you would see those numbers are to the right, and in the other case the numbers are to the left. But what does these numbers really represent, and what it really tell us about the soil? Now, if we just focused on case A, we would find that this profile has two main master soil horizons. It has an A horizon that is undergoing plowing activities and a C horizon. However, you would find that the C horizon was divided into C1, C2, C3, C4, and C5. Now, these C's has numbers 1, 2, 3 to 5, and all the numbers exist to the right. So what does this really mean? Well, basically, in real life, you might have a horizon like the C here, but it basically has distinctive layers. Like distinctive layers may exist within a master horizon like this. And these layers, all of them having the property of the C horizon, but they are a little bit different than the other ones because of changes, for example, or differences in the colors, maybe in the structure, or maybe in the texture and the feel. So we distinguish them by giving them numbers, and those numbers will be placed to the right of the horizon. You can have this condition also not only for the C horizon, but it can exist for any of the horizon as long as you might have distinctive layer within that particular horizon. Now, something else you would notice that the numbers basically are increasing if you go down. So usually how we do it, usually we give the first number like number 1 for the layer that is at the top, and as we go down we give it the other numbers like 3, 4, 5, like in this case. And you can also see this another example. So in this profile you have a soil that basically, or a soil profile that basically consists of 3 master soil horizons. You have A at the top, and then you have B, and then you have C. Now, if you look at B, it basically a B horizon with accumulation of clay because it's indicated by T. If you go back to the table which we have taken last lecture, T means clay accumulation. However, although this B horizon have clay accumulation, but there are some layers exist between or within this master horizon, and they are basically five layers. That's why we indicate them with numbers to the right of the soil horizons. However, the numbers that exist to the left of the horizon can tell us a lot of interesting stories about the formation and the history of that particular soil profile. We usually put the numbers to the left to indicate that that particular soil horizon is formed from a different parent material rather than the formation processes or the soil formation processes. In a normal case, we have A, B, C, for example. And these A, B, C horizons are formed because of the soil formation processes and factors. In the current case, you would see that you have AB, and then you might have also another AB, but you would have numbers to the left. So, to make it more clear to you, let's focus on the picture that you see in the slide. This is a picture of a soil profile that has been taken from Atlantic coastal plain in the US. This soil profile is basically closer to a stream or closer to a river. But once you look at it, you would see that the top 80 centimeter of this soil is basically formed due to a recent alluvium deposition from the river or from the... Now, if you go farther down, you would see, you would have a soil horizon that is indicated as 2CU. Now, if you go back to the table that we have taken last time, you would see that U means or indicate that this soil has human artifacts. And basically what this layer tells us that this layer having an artifact due to the human activities like glasses and so on. Now if you further go down, you would find 3C2, and this layer is a black layer, and if you distinguish it and if you dig on it, you would find that this black color is basically a charcoal depositions. How this charcoal layer formed? It was formed about 1,700 years ago, and it is basically related to the human settlement in this particular area. So when those people came to this area, they basically deforestate that area in order to do their agricultural activities. And to do that, they basically cut the forest and burn it, so they clear the entire land, and then they can grow their agricultural activities. And at that time, when the rain happens and it washed basically those charcoal materials to the river, and then it has been deposited in this profile. So now you can see that this layer goes back to a very old time. Now if you go farther deeper, you would find a layer that is indicated by 4C3. Now this layer basically has some shell materials, and these shell materials refer back to the Indian Americans who settled closer to the stream. And at that time again, when the rains happened, the stream washed out these shell and sea materials, and then it brought them back, it brought them here and deposited them at this particular time. Now the last layer is given by the number 5. You have AB, and then you have 5AB, and then you have 5BGB. Now remember, what does the P letter mean? The B letter means that it is a buried soil, and the G letter means this is a glade soil. So this is basically tell us that, or indicates, or it's a parent material or a soil that has formed when the river itself or the stream was exactly in this particular place, was flowing at this particular place. So at that time, all of this soil was fully saturated, inundated with water. So you can see how the numbers to the left can tell us the history of the soil and can tell us that each one is basically a different parent material, or each number is a different parent. Moving to the second point of this lecture, which is transition horizons. Now, what is transition horizon? When do we use them? And how can we distinguish them? And what types of transition horizon might exist in a soil profile? To answer all of these questions, let's again look at case A and case B. Now, I want you to pay attention to case A. In case A, you would see that it's a profile consisting of different horizons. But if we focus at the top, you would see that we have A horizon, and then the second arrow represent or pinpoints to the P horizon. But between these two horizons, N and P, there is something different. There is a layer that has the property of A horizon and B horizon. It's not exactly A and not exactly B, but it has a kind of mixing, and it exists between these two horizons. And this is, we call it a transition horizon between A and B, as in this case. Now, if you look to case B, you would find also that the first arrow indicate E layer, E horizon, and the second arrow indicate to a B horizon. But between these two horizons, there is a layer that is given by E/B, and this is another type of transition horizon. Now, to distinguish the differences between them and understand them more, let's see how they looks like. Now, in case A, the transition between A horizon and B horizon looks like this. It's like a smooth and parallel. So you can see that the arrow, or the arrow which I use here, the dotted line I used here is parallel. Whereas if you look to case B, you would find that the transition horizon basically the transition horizon have a properties of E and B, but basically they look like the transition, like the B layer or the P part is like a slash to the E one. Now, to understand more the transition horizon, well, basically the transition horizon exists in a soil profile as a transition between two horizons, and you can see that we indicate them with capital letters depending on the horizons that they are between. As in case A, they are basically represented as AB because it's a layer or a transition horizon between the horizon A and horizon B. In the second case, you would see that this transition is not parallel and smooth, but it's localized. So you would find that the properties of B is localized to the right side of the profile, whereas the properties of A is like this. And the transition between them, look at the color, it's like a slash. That's why for case B, we give it E/B. Now, you would also see something else. You would see that we write it as in case A, we write it as A, then B. So it's A, B. Can it be B, A? Well, yes. It depends on which horizon is more prominent, or which properties of the horizon it's more prominent in that transition layer. Now, if you look at the thickness, you would see that the property of A is more prominent than B in the transition horizon as in case A. That's why we write it A, B. But if the B properties is more predominant than A, then we can write it as BA. For the second case, you would find that the properties of E is more prominent than B in the transition horizon. That's why we wrote it E/B. But it can be the opposite. It can be B/E if the properties of E is more than B. So that's how the transition horizon. Very easy things. Now let's move to talk about the third point of this lecture, which is maturity and development of the soil. Do you remember in the past when I gave you an example and I told you that maturity of the soil is not the number of years? So you can find a soil which is 20 years old can be described as more mature than a soil of 100 years old, because maturity and development in the soil depends on the degree of weathering and profile development. So if I ask you a question, which one of these profile is more mature? Well, the number of layers can indicate for you one thing, but the most important thing that will tell you the maturity is basically the profile development. So you would see that the profile with more horizons is more mature than the one with only one horizon. And the second thing, the types of the horizon. The profile with more types of horizons would be more mature than the other ones. So for example, we can see that the fourth profile to the right is very mature because it has actually more numbers of horizons. It has 1, 2, 3, it has 4 master horizons compared to the other. We might ask ourselves a question like, are there any differences between a young and a mature soil profile in terms of their chemical status? More specifically, the mineral types, the fertility, and the amount of clay? Well, yeah, there are differences like this. So usually a young soil is more predominant of primary types minerals like quartz, feldspar, and others. However, when the soil becomes mature, its mineral content change and develop to a more stable form. They are basically changed with the chemical and the physical weathering, especially the chemical weathering, from a primary type minerals to secondary type minerals. That's why in a mature soil you would find more of secondary minerals like smectite, illites, etc. Now, when you talk about fertility, you can say in general that a young soil has lower fertility than a mature soil. And if you compare the clay content, you would find that a young soil would have less clay content compared to a mature soil. Because what happens with maturity, that with intensive physical and chemical weathering, the soil particles can be broken down into a very fine size, into the clay size, to be less than 0.002 millimeter in diameter, for example. And that's why you have more clay in a mature soil compared to a young soil. You may ask yourself another question. Well, now we know that intensity of weathering and profile development are the main reason for creating a mature soil. But are there any other factors, or are there any factors that can slow down this process and therefore slow down the process of soil development and maturity? The answer is yes. Any factor that can affect the process would slow down the soil development. For example, lower rainfall and relative humidity. When you have less water into the soil, you have basically less development, because water is very important for the especially for the chemical weathering. And water also, especially from the rainfall, is very important, because if you have a lot of rainfall, okay, then that rain can go deeper into the soil profile and create a deeper profile development, because water can dissolve a nutrient, can translocate things within the profile, can input something into the profile, and so on. Now, a second factor is basically temperature. If the temperature is very low, then you know from previous lectures that temperature is very important for the chemical weathering and also biological activities. So when you bring the temperature down, you basically slowing down the chemical weathering, and you are also slowing down the biological activities, which are very important for the soil development. Another factor is higher water table. Now, well, this is a kind of contradicting. You just told us that water is very important for the development, but now how can water act as a retardation factor? It depends. Now, in this condition, when you have a shallow water table, like what you can see from the second picture, it means that the whole profile is saturated with water. Now, this water means that all the pores are saturated with water. You don't have aeration, and that won't be good for all sorts of biological activities. You will not have microorganisms, or it won't be good for plants unless if those plants or biological factors can tolerate saturation condition. But in most of the time, most of the creatures, most of the things prefer a well aerated conditions, not a saturated condition. Now, parent material types can also affect the degree of weathering and the soil development. If you have a lot of quartz, like primary mineral like quartz, you would have a slower development. Why? Because quartz basically are one of the most resistive minerals for weathering. That's why to develop the soil and break it down into smaller particles and to create a lot of changes on it, you would need a very intensive weathering, and you would need a longer time to do the changes, because that mineral is very resistive. The amount of clay also is another factor. Now, if you look at the third picture, you would see that when you have a lot of clay, you basically slow down the water movement into the soil. And if you don't have a lot of water getting into the soil, you mean you are eliminating the water, which can create a lot of chemical weathering, and it can also basically translocate things and move things from the top to the bottom, dissolve things, and so on and so on. And not only that, when you have clay, basically you would have a smaller pore sizes, and by these small pore sizes, it might also affect basically plant development, or also affect the other organisms that they cannot find a space to stay in the soil. Another factor is the presence of toxic substance to plants. When you have these toxic substance, it will kill the plants. And once you kill the plant, you eliminate the impact of plant. You eliminate the impact of the roots. You eliminate how the plants can create pathways, can also affect the other organisms, and so on and so on. Topography is another important factor. You remember from the previous lectures, when we have a steep slope, then water movement over that surface becomes very fast, and therefore it can erode the soil and it won't allow a profile development, because most of the water that falls on a steep slope run over the surface, erode the soil. Now the final factor is disturbance, like the fire. Again, when you have a fire, like what happens in some of the forest fires, like what happened in Australia or Amazon or California, basically the fires will burn the forest, and therefore you eliminate the vegetative cover, you eliminate the forest, and that would significantly affect the biological life. It would affect the water movement, it would affect the macro and microorganisms that live in the soil, and it will affect so many properties that would basically lead at the end of the day to slow down the development of that particular soil profile. From the previous points, we have seen that the soil can develop and becomes mature from 4 different soil formation processes and 5 soil formation factors. Now the 5 soil formation factors are abbreviated by C ports, as we said previously. C, climate, parent material, organisms, reliefs, and time. And these 5 factors cannot be separated. All of them must act all together into the soil to create the development. However, in some of the cases, you might go to a place where you would see that you have the same parent material, you have the same climate, you have the same organisms, it's the same time. However, you might find some differences in the soil because of the topography. So if you go to the summit, the soil might be different than going into the floodplain in the topography. And in this condition, we call these changes or this development, or this soil is developed due to the variation in relief, we call it catena. The second type is basically chronosequence. So what is chronosequence? Chronosequence refers when you have a soil that is basically differ because of the time, but all other soil factors are equal. A lithosequence when you have differences in the parent material, but all other factors are equal. Climasequence when you have all other factors are equal except climate, and because of the climate you might create variation in the soil. Biosequence is a soil group that basically differ only due to the differences in the type and the number of the biological activities, like the organisms and like plant. Okay, I guess after the first part, let's take a break to find something interesting to learn and maybe to taste at this time. Have you heard about edible soil layers? Well, see the pictures, click the link below and explore what it exactly is and how can we prepare it at home. So take a break and do it. Alright, so I think you are more fresh and ready to continue with the last part of this lecture. If you look at the soil and inspect it, you would find that it basically consists of 3 different things. It consists of mineral particles, which represent 48%, and then you have 2% organic matter, and the last part is basically the pore spaces. Now, the pore spaces can be either entirely filled with air, or entirely filled with water, or filled with air and water. So in a well aerated condition, you would find 25% air and 25% water. In a saturated conditions, all the pore spaces are filled with water. And in a very dry condition, mostly that the pore spaces are filled with air. Now, how all of these components or these three parts affects the physical properties and why it is really important to be explored in a soil science. Let's go and dive more into the soil and discover it. The physical properties of the soil indicates the appearance and the feel of the soil. Therefore, it consists of the color, for example, or the texture, which describe how it feels, or the structure, which is basically the shape of the soil, how heavy or how dense is the soil, which describe the density and porosity, how hard is the soil, which describe the strength, or how wet the soil, which describe the water content, or how hot the soil, which describe the temperature. These physical properties of the soil are fundamental and very important for the sustainability. For example, the physical properties indicates the sustainability of the soil for agriculture. The physical properties determine the sustainability of the wildlife and plant. The physical properties would tell us whether this soil is suitable for building or not. And it would also tell us whether this soil can be easily eroded or not. The physical properties control the movement and the storage of the water. And not only that, but also it can control the movement and the storage of nutrient as well. And the physical properties can further affect the chemical and biological properties of the soil. And that's why we have to study. One of the most important physical properties of the soil is the color. Now, when you look at different soils having different colors, it can tell you a lot more stories deeper than what you only can see, because the color can tell you about the chemical content of that soil. The color also can describe for you the condition, whether that soil is a well aerated or not well aerated, whether that soil having a wet condition or a dry condition. Basically, the color is like the paint of the wall. So the color can describe for us the type of the parent material. The color can tell us about the amount of organic matter. And a red color, for example, in the soil can tell you that you might have a lot of iron oxide on it. The color also can describe the aeration of the soil. So if you have a darker color, then it can indicate for you that your soil is wet. And if the color developed to be more to a green side, then it can tell you that your soil is wet for a long time. Or if the color is light, then it can tell you that your soil is dry. It is true that from the soil color we can tell a lot of stories. So if you just look at the first profile, you would see that this profile is dark in color, it's basically black, and you would find that it's an organic soil. The second profile is a young soil profile in the floodplain, which receive frequent sediments. The third profile is red in color, and this profile is basically in a well-drained soil, and because of this, the iron oxide on it, the iron was oxidized and turned into this red color. So it tells us about the aeration and the degree of weather. But how can we identify and classify the color of the soil? Well, basically, we would use something called Munsell color chart, which is basically like a book. Now, in the Munsell color chart, there are three basic important components. Hue, which basically describe the different colors, the color of the rainbow. The value, which describe the blackness or the whiteness. So if you have a value closer to 0, it means black. And finally, the chroma, which describe the purity of the color. Now remember, a purity of the color is basically the soil becomes naked, or when you remove the paint of the soil, when you remove all of these materials, it goes back to its native color, which is almost pure and gray. To understand these three components, let's look inside one of the pages of the Munsell color chart. Now, if you look at this example, you would find that at the top right corner you have the hue. Now, the hue is written as 10YR, so Y indicates yellow and R indicates red. And each page of the Munsell color chart have a unique hue value. Looking at the left side of this page, you would find the value. Now, as you can see that if you go down, the value becomes less and the color becomes darker and darker. And if you go up, the value increases and the color becomes brighter or whiter. Chroma is the third component, and chroma, as we said, describes the purity of the soil. So if you move to the right side, or if the chroma value increases, then the soil becomes less pure compared to if you move to a smaller chroma value, the soil becomes more pure. It will return to its original color without the paint. Now we know more about the soil color and what does it mean, but what are the three factors that can influence the soil color? Well, the three factors as follow. The organic matter content. When you have more organic matter content, the color of the soil will become darker and darker. The second condition is, or the second factor is the water. So when you have more of water, the soil becomes darker and the rate of decomposition of organic matter and oxidation will be reduced. The third factor is the oxidation state of iron and manganese, because these two minerals, when they change in the oxidation status, they reflect a different color in the soil. And to understand this more, let's go to the next slide. So how can the soil color indicates the change of the chemical status of iron, for example? When the soil has a lot of iron on it and the soil becomes well aerated, then iron will be oxidized, and when it is oxidized it will reflect a red-brown color. Now if this soil becomes saturated, then it will become in under anaerobic condition, and at this stage iron will be reduced, and due to this reduction, the color will change from red brown to gray bluish or gray green color. So we can see now that the color can even tell us about the change of the chemical status of some of the minerals like iron. And so that's all for this lecture. I hope you enjoyed it, and I hope you explored more new things in the soil. So see you and take care. Bye.